Hello students, today we are going to discuss about the general characteristic of transition elements part 2. Under this video we will cover the topics which was left like oxidation states, reduction potentials. So let us start this topic with very good thought. I can do things you cannot, you can do things I cannot. Together we can do great things. Mother Teresa. So let us start with the learning outcomes. So here in the general characteristic we would like to discuss about electrode potentials, oxidation states, formation of colored ions, magnetic properties, catalytic properties. Apart from that we will be having interstitial compounds, complex compounds also. So here is the list, general brief idea about the characteristic of transition element. As we have discussed in the last video, that except for mercury, which is a liquid at room temperature, all other elements shows high melting point and boiling point, and characteristic of metals like malleability, ductility, high density. And next is about the variable oxidation state. For example, transition element like iron. Iron exists in class 2, class 3. Manganese exists in class 4, class 6, class 7. So similarly, they show catalytic behavior also. Like catalysts is used, nickel, platinum, titanium. These are used as catalysts. Their compounds are colored, like manganese, chromium, iron, copper. These are colored compounds. And they are having tendency to form complex like tetramine silver complex, tetramine copper complex. So these transition elements are having specific characteristic of forming complex compounds or coordination compounds. They form alloys and interstitial compounds. We are going to discuss these small factors which are very, very important. So let us start with the first one, that is electrode potential. So see here, what is the meaning of electrode potential? If you see from here, M2 plus to M, M3 plus to M2 plus, what is the meaning for that? It is a reduction. Reduction means gain of electron. 2 plus means to M means M2 plus gain 2 electron to form M, means tendency to get reduced. So you know that metals normally lose electron. So metals lose electron, therefore they tends to oxidize, not tend to reduce. Therefore there shows the negative values here. But here copper is having strong tendency to get reduced, not to get oxidized. Copper is having tendency to gain electron rather than lose electron, copper ion specifically. So here you can see that most of the transition element shows negative value of reduction potential, which signifies they are metals, they are having tendency to lose electron, but only the copper is there which is not having that much tendency to lose electrons, having tendency to gain electron. Copper ion is having tendency to gain electron. So why it is so? We will discuss in detail. So let us understand first about the standard electrode potential in detail, then we will go for that question. So what is the meaning of electrode potential? It is the measure of the total value of enthalpy change. Actually it is the combination of three changes which we are going to discuss now. So here electrode potential depends on what? It depends on enthalpy of atomization, means to form atom, to break the bonds, the energy required to break the bonds. Second is in regard to hydration enthalpy. That means that the hydration enthalpy, when a substance, when an ion gets in contact with water, it releases energy. That is known as hydration enthalpy. So these factors like ionization energy, enthalpy of atomization and hydration enthalpy, these three factors combinedly decide the standard reduction potential values. The more stable the oxidation state is, if for example E0 value is negative, to that substance will be more stable. For example, if I say that X and Y are two elements and they are having 2 plus 2 reduction values, if it is one is having minus 5 and one is minus 2, so minus 5 value would be more stable. This is the general trend. So now here as regard to copper again, so why the copper is having positive E0 value? Here it is reflected here also. So copper is having positive value. That is the reason that it cannot liberate hydrogen from acid. So it's not having tendency to lose electron, it's having tendency to gain electron. That's why it cannot remove hydrogen from acids. So the point is now why. So here what is the basic point is, it is having high delta HA, means enthalpy of atomization is very high in case of copper, and it is having low value of hydration enthalpy. So that is the reason that E0 value is positive. Okay, greater the amount of energy required to transform copper into copper 2 plus, means that is not having any tendency to that change into copper. Reduction value is more, positive reduction value is more, and the tendency for getting oxidation is less. So here also see that copper plus copper 2 plus and copper plus to copper. So here this is a disproportionation reaction where copper plus changes to copper 2 plus means loss of electron, and here copper plus changes to copper, it means gain of electron, that is copper. So here stability of copper ions aqueous because aqueous only this delta H value hydration will come into play, and this is copper ions stability, this is more stable. Why more stable? Because delta H is hydration value will be low. So due to much more negative value of delta H hydration, means much more negative value means the negative means delta energy is released, large amount of energy is released, that is the meaning. Okay, as compared to this copper ions to copper, it means it's having tendency to move towards copper 2 plus to copper with to get hydrolyzed, which more than the compensate with the second ionization enthalpy of copper. So here next is the point. Let us see and just discuss about the reduction values, like minus 1.18, minus here it is. So this irregular is there, irregularity is there. So these are not regular, and it is, I told you already that this value is not deciding only on the ionization energy. It depends on the three factors: ionization energy, atomization, and the hydration. So hydration further depends on the size of the ion. So here all these factors are collectively deciding. That is why there is not a regular trend, that trend is irregular. Okay, because this is a combination of ionization enthalpies, hydration enthalpies, and the ionization energies. So that is the reason, so why there is irregular trend. Next is stability and hydration. So how, or E0 value, how we are going to explain. Stability of half-filled subshell in Mn2 plus and the completely filled D10 configuration is more. So sometimes we say that Mn2 plus, let us say Mn2 plus is there, so 4s2 3d5 was there earlier, and then when 2 electron is lost, 4s0 3d5. Now here 5 partially filled up d electrons are there, and in case of zinc 2 plus, we are having 4s2 3d10 configuration of zinc. Now after removing 2 electron, 4s0 3d10, so this is fully filled configuration. Mean to say that Mn2 plus is having 4s0 3d5, and here it is 4s0 3d10. So the point here is how it is related with the E0 values. E0 value for nickel is related to highest negative value of delta H, because the value here we are talking of value minus 0.25, and if you are talking of manganese, that's minus 1.18. It's due to the stability of what? Stability of half-filled d orbitals. Okay, so this is overall deciding the stability. The low value of scandium reflects the stability of Sc3 plus. Mean to say that, let us say this we are talking is, here scandium value is not given. So scandium value is low because you see scandium is having atomic number 21, argon 18, 4s2 3d1. So when say removing 2 electron, 4s it is 0 3d1. So now 1 electron is there. It tends to lose electron to form Sc3 plus by attaining the D0 configuration. So similarly, zinc, after removing 2 electron, it attains D10 configuration of zinc 2 plus. So similarly, Mn2 plus, after losing 2 electron, it attains 3d5 configuration. So which is more stable. And here this, because that is the reason that stable, because it is partially filled or fully filled configurations, particularly Mn2 plus and Zn2 plus. Okay, and similarly here also, if you are talking of Fe3 plus is more stable. Why? So you can just write the electronic configuration in each of the case. Argon 18 4s2 3d6. So if you remove 2 electron, 4s0 3d6 would be there, and if I am removing 3 electron, 4s0 3d5. So means to say that here the electronic configuration is argon 18 4s0 3d5. This is the stable configuration. So that is why this ion is stable, because it is having, after losing electron, it is attaining the stable electronic configuration. So now comes out to be the oxidation states. So now here see, all the oxidation state, everything is dependent on the ionization energy and the electron which we are going to remove from the outermost shell and the penultimate shell. And you know, if I am now talking of scandium, we are having electronic configuration of argon 18 4s to 3d1. So now electron first will be removed from 4s because it is the outermost shell, and it is outermost shell, so energy level is high already. I need less amount of energy to remove this electron, and then again 3d electron will be removed. For example, if I am removing these 2 electrons, so oxidation state is +2, and if I am removing this 3d1 electron also, it will be oxidation state will be 3. Similarly, here also titanium, I can remove this 4s2 electrons and 2 electrons from 3d, so it resulting into the oxidation state of +4. Now in this case of vanadium, we can remove 2 electrons from 4s, that is 1 + 2 oxidation state. If I am removing 2 electrons from here, 1 from here, the oxidation state is +3, and if I am removing 2, it will be 4, and 2, 3, it will be 5. So that is the reason that the transition element shows variable oxidation state, because the electron can be lost from 4s2 electrons, 4s2 electrons and 3d electrons. So depending upon the electrons can be removed from outermost shell and penultimate shell. That is the sole reason that why transition elements are showing variable oxidation states. Okay. Now, so I will suggest you that you should write the electronic configuration and once check yourself, because this is very important that once you do the practice, it will be more easy and convenient for you to understand each and every concept in a nice manner. So this we have discussed about the variable oxidation. Why? Because electrons can be removed from 4s or 3d, outermost shell or penultimate shell. Similarly, iron 2 + 3 +, copper +1 + 2, chromium 3 + 6 +, manganese +4 + 2 + 7. Okay. Now these are the oxidation states. So you can see from here the most common oxidation state 3 is the most common here, and here also 3 is there, 3, 4. And you can see from here the ruthenium is having oxidation state of +2, 3, 4, 5, 6, 7, 8. And here also 2, 3, 4, so 2 not there, 3, 4, 5, 6, 7, 8. And if you are talking of manganese, 2, 3, 4, 6, 7. So maximum oxidation state we can find here is +8. Okay. So this please keep in mind. And silver is having the most common oxidation state of 1. Now, oxidation shows variable. This we have discussed already, because electron can be removed from outermost shell NS and the penultimate shell. This results in the variable oxidation states. Now here, so manganese, we have seen that manganese can show +7 oxidation state. How? For example, if you write the electronic configuration of manganese, if you write argon 18 4s2 3d5. So now 4s2 electron when you are removing, it will attain +2 oxidation state, and if we are removing 3, 5 also, total 7 electrons are removed, so oxidation state is +7. So means to say that when an electron is lost, ultimately the ion is getting stabilized. Ion is attaining partially filled d orbitals or half filled or fully filled. So that is the reason that these ions are stable in the aqueous solution as well as in the elemental state. Elements in the beginning of the series exhibit fewer oxidation state, have a small number of electrons in which they lose or contribute. For example, if it in the start is there, like only 3, 4s2 electrons will be removed, or 3d1 or 2 is removed, therefore it cannot show higher oxidation states. So elements at the end of the series shows fewer oxidation states. For example, zinc, we are having very less, only +2 oxidation state is there. Why it is so? Because there are d orbitals are fully filled, so that brings the stability. Okay, so because until and unless they are having partially filled d orbitals, it is easy to remove as compared to fully filled. So that because that is not involved in the bonding, therefore it will not show the oxidation state. It is only showing oxidation state when higher electronegative element are combined with that, like oxygen and all that. Okay, so here stability of halides of first transition series. So you can see from here, chromium can show the +6, +5, +4, +3, +2, and vanadium can show that 2, 3, 4, 5, and similarly manganese can show 4, 5, 2, and this type the oxidation states can be shown with fluorine. And see here, the transition and metals also exhibit the highest oxidation state in their oxides. As I told already, the oxygen helps in the increasing the oxidation state in doing the oxidation of the metal. The ability of oxygen to stabilize higher oxidation state are much higher than fluorine. We can see from here the examples. Here only very few compounds are there, Mn, F4, F3, F2. So when you will find the oxygen will be having lot many the oxygen based compounds with the transition metal. So here you can find that highest oxidation state of manganese is +7, that is in case of Mn2O7. And you can see from here they have not shown any +7 oxidation state with the fluorine. Okay, so oxygen is having more tendency to oxidize the metal to show in higher oxidation state, because oxygen can form multiple bonds but fluorine cannot form, or halogen cannot form multiple bonds. The oxides of 3D transition cell series are given here. So we will discuss these are the oxides of transition elements. So here Mn2O7, MnO2, Mn2O3. So their number of oxides are formed in higher oxidation state also, because oxygen is having tendency to form multiple bond, which results in the higher oxidation state. Now this was a very important question. It is related to the ionization energy, with the topic we have covered in the previous video. So question can be asked in this manner, that why nickel +4 compounds are less stable than platinum +4, and why nickel 2+ compounds are more stable than platinum +2. So it depends on the ionization energy. Ionization energy, we can predict the two metals in a given oxidation is thermodynamically stable or not. So if we talk of any metal, if we remove 4 electron, then the ionization energy considered would be IE1 plus IE2 plus IE3 plus IE4. Means successive ionization energy we have to add. So now, in case of nickel, if you are removing 2 electrons, the sum of the successive ionization energy is 2.49 times per 3, but platinum it is 2.66 times per 3, means to say that nickel +2 needs less energy to remove the 2 electron as compared to platinum. But in case of nickel +4, if I want to remove 4 electrons, the energy required is 11.29 times per 3 kilojoule per mole. But in case of platinum, it is 9.36 times per 3 kilojoule per mole. So mean to say that platinum needs lesser amount of energy to remove 4 electrons. Therefore, platinum +4 substance compounds are more stable as compared to nickel +4 compounds. And along with that, nickel +2 compounds are more stable than platinum +2. So this we have discussed already. So this is about the oxides. Oxides, as you know that lower oxides would be basic and higher oxide would be acidic. Okay, and intermediate would be, like for example, if you are talking of chromium, this is +2, this is basic, and here it is +3, it's amphoteric, and here also +4 amphoteric, but here it is +6, so this is acidic. So higher is the oxidation state, the acidic character will prevail when metal oxides are there. So you can see here, lower oxidation state metals are basic, higher oxidation states are acidic, intermediate can be amphoteric also. Okay, so see, this type of questions are important, can be asked in the exam. So disproportionation reaction we have done number of times in P block also, when a particular oxidation state become less stable relative to the oxidation state of one lower, one higher. Or in a simple word, if I will calculate the oxidation state here, it would be, let us say 2 here, so -8, 6, it would be 6, and here also if you talk of 8 and it is 7, 6 changes to 7, it means oxidation, and here 4, so 6 changes to 4 means manganese is undergoing oxidation as well as reduction. So substance undergoing oxidation and reduction in a same the reaction, that reaction is called disproportionation. So now we are going to discuss about the chemical reactivity. Transition metals vary widely in their chemical reactivity. Many of them are sufficiently electropositive, dissolved in mineral acid, and few are noble also, they don't react. Metals of first series with the exception of copper are relatively more reactive, because you know that E0 value is negative, so therefore reactivity depends on E0 value also, and oxidized copper is not as such reactive. Okay, fine. So this is about the E0 values, indicates a decreasing tendency to form divalent cations across the series, because you have seen that M2 plus 2M is negative. It is not having tendency to gain electron. Therefore, reactivity is less. Increasing the sum of first and second ionization enthalpy. So less negative value means that increase in the high ionization energy is required to move 2 electrons. Okay. Now, so here in this reaction, you can see from here 2 plus is changing to 3 plus. Mean to say that E0 value for the redox couple 3 plus to 2 plus shows that Mn3 plus and cobalt 3 ions are strongest oxidizing agent. What is the meaning for that? Just understand that. Mn3 plus means 4s0 3d4, and 3 plus changes to 2 plus means what? 3 gaining of electron. It will attain 3d5 configuration. If it is attaining 3d5 configuration, it will get stability. Therefore, gaining of electron is reduction and acting as oxidizing agent in aqueous solution, because hydration effect will come into play. Similarly, cobalt 3 plus, iron, nickel, cobalt. Iron, nickel, cobalt means 27, 26, 27, 28. 28. 4s2, 3d8. And if you are removing 3 electrons, let us say 4s0, 3 to 7. Now here, what is happening is cobalt, we are having splitting. Splitting means 3 orbitals in the lower energy and 2 orbitals in higher energy. So now we are having iron, cobalt 4s2, 3d8. Now it is changing into 7. So 7, it can gain 1 electron and it become 8. 8 means 6 electron in the lower d orbitals and 2 electron partially filled in the reducing agent. If gain oxidizing agent, it will again attain the stability. Now formation of colored ions. So color is why? Why is the color substantial? When a substance absorbs energy, the electron in the d orbital excite to higher energy orbital. So there d also now it is splitting takes place. As we were discussing in the previous slide, splitting of d orbital takes place, 3 orbital in one lower energy and 2 orbital in higher energy. When electron jump from lower energy d orbital to higher energy orbital, it absorbs higher energy. It absorbs the energy, and the energy of excitation that is given by the frequency of the light, like Vibgyor, violet, indigo, blue, green, yellow, orange, red. Violet is having lower wavelength. Lower wavelength means high energy, and higher wavelength means lower energy. So it depends on the ionization energy. If ionization energy is less, the red will be sufficient. If ionization energy is more, violet will be required. So this, after absorbing light, the color observed. What is the color observed? It corresponds to the complementary color of the light absorbed. Which color is absorbed? The complementary color will be exhibited. It will be shown. The frequency of light absorbed is determined by the nature of the ligand. Nature means surrounding, which ion is surrounding the metal. So this is the basic. So mostly transition element shows color except zinc 2 plus and cadmium 2 plus, because they are having fully filled d orbital. There is no electron transition possible. This transition is also known as d-d transition. I was talking about the splitting of d orbital. This is the meaning of splitting of d orbital. These d orbitals are 3 d orbital, dxy, yz, zx, and these 2 d orbitals are x square, y square, and z square. Whenever electron jump from here to here, so there is transition after absorbing the energy. Once the energy is absorbed, according to the energy absorbed, some complementary color will be shown, exhibited. So that represent the color of that ion. Okay. Now this is the color ions. Like you can see that if any example you will feel here, like let us say scandium is there. Scandium, argon 18 4s2 3d1. So now you remove 3 electron, there is no electron in d orbital, then how d transition will take place? So if d electrons are not there, so how transition is possible? Similarly, here fully filled orbitals are there, zinc. There is no partially filled d electron, then how transition will be possible? If transition is not possible, then how color will be possible? Okay, so the means to say that any ion will show color because of the presence of partially filled d electron. Then only transition from dxy, zx by dxy, yz, zx to x square, y square, and z square is possible. So magnetic properties now. So substance which contains species, atom, ions, and molecule with unpaired electrons. So magnetic property also related with number of unpaired electrons. More the number of unpaired electrons, more will be the paramagnetic character. Okay, and they, even though if they remove the magnetic field, then also it will show magnetic character. And strongly attracted is ferromagnetic character. Substance which do not contain any unpaired electron are called diamagnetic. So this we are studying in solid state also, first chapter. So next is because it is due to unpaired electron. Unpaired electron, this paramagnetic character is due to unpaired electron, and it is calculated mathematically by using the formula under root of n into n plus 2 Bm. Bm means Bohr magneton. Okay, n is what? N is number of unpaired d electrons. This we can calculate. For example, let us say we are having chromium. Chromium 4s1 3d5 is there, 4s0 3d4. 4 electrons are there. 4 when you substitute in the formula under root n into n plus 2, it will be under root 24. Under 24 will be 4.9. So this way we can say that. And this is calculated by that formula, this formula under root n into n plus 2, and this observed value is just equivalent to that of the calculated by the formula, spin calculation formula. Now here you can have to find the 25. So here 4s2 3d5. So 4s2 3d5 means 5. If divalent ion is there, 4s0 3d5, and 5 unpaired electrons, d orbitals, and 5 into n plus 2 7, 35 and root 35, and 35 comes to 5.92 Bm. Bm means Bohr magneton. So the next property is regarding to catalytic property, catalyst activity. Catalytic activity of this is the important characteristic of transition metal. It is ascribed to the ability to adopt multiple oxidation states and to form complexes. Because transition elements can exhibit multiple oxidation states, they can decrease the activation energy, they can form the intermediate complex, they can change the path of the reaction, it decreases the energy of activation, that's why resulting the catalytic action. So catalysts uses different examples are using different catalysts, we know already. So this is a sodium thiosulfate reaction, iodide, iron is the catalyst used, here oxidation of iodide is taking place to iodine. Similarly ferric is changed to ferrous, ferrous is changed to ferric, so different catalysts are used in this reaction. Now here catalytic property, why transition element shows catalytic behavior? Because of incomplete or empty d orbitals. Incomplete, it leads to the helping in the stability of variable oxidation state, and it provides large surface area, variable oxidation state, ability to form complexes like with the iron, nickel, vanadium, platinum, molybdenum, cobalt. So now the next property is complex formation. Complex means coordination complex. Transition metal tends to good Lewis acid. Lewis acid is a acid which is a metal which can gain lone pair of electron. Why it can gain? Because of the presence of empty d orbitals. Once the empty d orbitals is there, 2 electrons can be gained from the ligand. What is the ligand? Ligand is which is a donor. So metal is a acceptor, lone pair acceptor. Lone pair acceptor is Lewis acid. Lone pair donor is Lewis base. Lewis base is ligand, and in this reaction Ag is acting as a Lewis acid and water is acting as a Lewis base, so thereby forming the complex compounds. Complex compounds are there in the square bracket always. We have to put square bracket and charge outside plus. So Ag is the central metal atom, water is the ligand, and 2 is the coordination number. Okay, so more detail we will do in the next chapter, that is coordination complex. Now this is just the example. This is, for example, this is a complex and square bracket you can find here. This is the outer side chlorine, these are known as counter ions, and water is a ligand. How many are there? 4, so coordination number is 4. Thus copper is central metal atom, and this bond represents the coordinate bond. Okay, so this lone pair is donated by chlorine towards copper. This is lone pair donor, that is Lewis base, and this is lone pair receptor, that is a central metal atom. Okay, so this is the basic thing. This is a detail has been given. Transition metal is central metal atom. Ligand which can donate lone pair, it's also known as Lewis base. This is Lewis acid, and again these are forming ions, and outside ions are known as counter ions. Okay, more detail you will do in the next chapter. So coordination compounds, why the transition metals are forming coordination compounds is because of the vacant d orbitals. Because if vacant d orbitals is there, then only ligand can donate lone pair of electron towards itself and forming the coordinate bond. Smaller size of central metal atom, high charge on cation. Because charge is high, then only electron can be received in good manner. So the next and the few left is interstitial compounds. Interstitial compounds means when a small amount like small atoms in small amount like hydrogen, carbon or nitrogen are trapped inside the crystal lattice. You know that crystals are having voids. So voids will be filled by using this interstitial compounds. These are non-stoichiometric. Examples like titanium carbide, manganese Mn4n, Fe3H, VH 0.56 and TiH 1.7. What transition in properties brings about this by this interstitial compound is there, because the space is filled, then packing efficiency will be more. They are having high melting point now, higher than those of pure metal. They are having hard properties and they retain metallic conductivity and chemical inertness also increases. So these are the interstitial, because of the space, the vacant space will be filled by the atoms of smaller atomic size of boron, nitrogen, small atomic sizes. Now the next, this is again the same. They are non-stoichiometric and the properties are changed, they are becoming harder and less malleable and ductile. Now the next is alloys. Alloys, you know that it is a solid solution. Alloy is a mixture of homogeneous mixture of solid and solid. Why we are doing? To improve strength. Examples like gold, bronze, brass, sterling silver. So these are the examples. And you know that alloys, why the transition metals are forming alloys? Because they are having similar atomic size. Because one atom can displace from the crystal lattice and take space of other atom. So this is the reason that why transition metal can form alloys. And other examples of alloys are like ferrous alloy, chromium, vanadium, tungsten, molybdenum, manganese, used for the production of variety of steel and stainless steel. Alloy of transition metals with known transition metals such as brass, bronze also possible. So why it is so? Because of the similar atomic size, because metal can replace each other in the crystal lattice. So let us discuss some of the questions which we have discussed so that proper understanding is there. Why is chromium 2 plus reducing and Mn3 plus oxidizing? So we can just think of the electronic configuration. If you talk of chromium 2 plus is having 4s1 3d5. When 2 electrons are removed, 4s0 3d4. Now you just think that what it will happen, what it will do. It can lose 1 electron to form 3d3 configuration. As I have just now discussed that 3d3 means the d orbitals, the 3d orbitals will be having partially filled configuration and this will be having T2G level, 3 electrons partially filled. On the other hand, from manganese 2 plus to 3 plus means that, for example, let us say manganese is having 4s to 3d5. 4s0 3d5 after removing 2 electron, and 3d Mn3 plus if you are talking of, that will be 3d4. So 3d4, once you are gaining electron, Mn3 plus changes to Mn2 plus, which results in the formation of half-filled electronic configuration of d5. Because only thing I would suggest you is you just write the electronic configuration of these 2 ions, then you will come to know. And in this case, chromium case, you have to show this one. So you have to show the splitting, like 1 electron will come here in this case of chromium and 0 electron in case of chromium. So then you can say that it's partially filled d orbital. That's why the stability. For the increasing oxidation power, please be clear with the oxidation power is what oxidation power is tendency to gain electron. And you know that, see here, +7. Here it is +7 oxidation number. So what we have, due to increasing stability of lower species, means after gaining electron that would be more stable. 7 Mn7 Mn6 it changed to. So that will be more stable. That's the reason that will be having more stability. Okay. The following will be colored. So this is very important question. Now you can see that you have write the electronic configuration. If you see the d unfilled electrons are there, you will say that it is showing the color, otherwise no. So in this case, you can see from here titanium 3d plus 1, vanadium 3d2, copper 3d10. So copper will not show here. And similarly, ferric can show, manganese can show. So this is where that scandium cannot show here. Okay, and copper also, because there is no DD transition. So hopefully you knowing all the questions which we have discussed and understood the topic. Please do revise each and everything. And what for the session again is, I can do things, you cannot. You can do things, I cannot. Together we can do great things. Mother Teresa. Thank you.